Today we will discuss geometric random variables. We spent chapter 7 talking about what I'm calling just a normal random variable. That's just some variable that has numerical values that we could use the chart to find the mean and standard deviation. We talked in 8.1 about binomials. That was when we had a fixed number of trials and we either succeeded or we failed, and we asked questions like, what's the probability that I get 4 sevens out of 20 rolls of the dice, something like that. Geometric, today's topic, is very close to binomial, except with this variation. We are going to let the variable be the number of trials it takes for your first success. Okay, so whereas in binomial, I know I'm going to roll 20 times, and I want to know what's the probability that I get this many sevens, this many successes. In geometric, I know there's only going to be one success, and I'm going to roll until I get it. And the question would be, what's the probability that my first success happens on the 5th roll, for example? In terms of the graph or in terms of the distribution, a binomial is going to look kind of like this. If x is the number of successes, we're going to always have 0 as an option up to however many trials we have, because you could succeed 0 times or you could succeed all of the times. Geometric's going to be a little different in that there is no 0 option. I should have called that y because I'd used x, y, and z earlier, so I'll call that one y and this one z. If this is the case, I'm starting at 1. And there's a probability that I succeed on my first try and on my second try and so on. The interesting thing about the geometric is technically it goes up to infinity, because if you have a certain probability of succeeding and a certain chance of failing, theoretically you could keep on trying forever and never succeed. And most things eventually you'll succeed, but there's a slight probability that you keep going on and more trials, so this histogram would keep going on. Another fact about a geometric distribution, the one trial option is always the tallest bar. That's always your most likely outcome, which kind of seems like it might not be true. What if you're doing something that's difficult to do? What if I'm trying to roll a 12 with 2 dice? That's a 1 out of 36 chance. Even though I'm probably not going to do it in one try, 1 is still most likely. Think about it, because it's got to step down. How do you get from term to term in a geometric? All right, out to infinity. Well, if I succeed, whatever the probability of success is, that's the chances that it happens in the first trial. In order for my success to happen in trial number 2, I had to fail once and then succeed, QP. And since Q and P are both fractions, QP has to be smaller than P. Think about that. If you're multiplying P by a number less than 1, you're making it smaller. The third trial would be Q squared P. In other words, fail, fail, succeed. 4 would be 3 failures and a success. It makes a lot of sense, and it just follows that pattern, which means the formula for geometric is a lot simpler than it was for binomial. The probability that my first success, we could use R or we could use K. I think your formula sheet uses K for binomials and geometrics. Usually it books, and I use R. So we'll say this is the first success, happens on the rth trial, that it takes me R times to get a success, is fail R minus 1 times and then succeed. Let me actually, I'm looking back at it, let me change this to N and N. I'm going to fail N minus 1 times, because N is our number of trials. Where it used to be given, now it's part of the process, figuring out how many trials it's going to take. So this one, like I said, it's in your calculator, but usually it's just as easy to do it another way. This example question that I had up here, let Z be the number of trials it takes me to roll a 7. Okay, so example. What's the probability that my first 7 comes on my 5th roll? Well, in order for x, the value of the variable, to equal 5, I need to fail 4 times and succeed once. You remember from our dice sample space, there's a 5 out of 6 chance of not getting a 7. I need that to happen 4 times, followed by just to the first, and you don't need that first power there, you can just put 1/6. So this is geometric probability, a lot simpler than binomial and easier to use. Okay, so the other 2 questions. On average, how long is it going to take me to get a 7? And then standard deviation, the 2 formulas that we had for binomial. So mean, the average number of trials in order to get a success is 1 over p. So when they're fractions, that kind of makes sense. Think about this. If you're trying to roll a 7 and there's a 1 out of 6 shot that happens, 1 over 1 out of 6 is 6 over 1. So we would expect, on average, to have to roll 6 times. With binomial, usually your expected value was your tallest bar. Not always, but usually. With geometric, that's not the case. All right, remember, 1 is always your tallest bar. But on average, it's going to take me 1 out of p, or in the case of the dice, 6 tries to get my success. Standard deviation, actually, let's make this in terms of variance first. The variance of a geometric is q over p squared. All right, you don't need to worry about real-world significance like it usually is with variance. Standard deviation, by the way, square root of q over p. So we've got 1 over p and square root of q over p for our mean and standard deviation, and then variance, just square that if you need it. So the type of questions you'll be looking for now, look for a question where it says, how long is it going to take me to succeed? How many trials? What's the probability that it takes this many trials to succeed? We've got our main formula of the day here, fail, 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 succeed, and then our mean, variance, and standard deviation below. Okay, there's one more little formula that they kind of do some of the background work and get it out of the way for you. They can ask you a question in this wording, and you could probably figure it out with the current formula, but they just kind of sum it up for us. The probability that it takes more than n trials to see the first success. Sometimes a real-world situation, you would want to know, I don't really need to know the probability that it takes 3 tries or 4 tries. I just want to know what's the probability that it's going to take me more than this many times to see my first success. The probability that the number of trials is greater than n, whatever you need n to be, is just q to the n. Think about that. It makes sense. If I need to know, say I'm rolling dice, I want to know what's the probability that I can roll 5 times before I see my first 7. Or let's say I'm trying to scheme roulette and I want to know what's the probability that it's going to take me more than 5 rolls to get my first red result. Well, if it's going to be more than 5 tries, that means I had to have 5 failures, first of all. Then all of the other possible outcomes are put together, but the one common thing is that I failed 5 times. Then I might succeed on the 6th or the 7th or the 8th. Those are all wrapped up into this formula. But this is the probability that it takes over n trials to succeed. And notice this is x is greater than n, not greater than or equal to. So if you want to know the probability that it's going to take you more than 5 tries, so you're going to have to take that 6th trial, you're going to do q to the 5th. Whatever the probability of failure is raised to the 5th. So because of all the similarities between this and binomial, that's really all I need to say about it at this point. You've still got your independent trials with success or failure. It's just a different way to define the variable. It's not fixed number, and I want to succeed this many times. It's I don't know how many trials, and I want to know what's the probability that my success is going to happen on this particular trial. Okay, so this wraps up our unit. We've done 7 and 8 together. So in class we'll start reviewing for our test, and I'll see you then. Out.